Okay, so percent yield. Now, we know the law of conservation of matter says that what we put in should be what we get out. Matter is neither created nor destroyed. But what happens is during a reaction, sometimes it's a single step. You go to collect your product, maybe something didn't react completely. Maybe you didn't let it go long enough. Maybe there was a contaminant in there and a side product formed and you've got two things competing with each other. Maybe you have to pour something from one container to another and something gets left behind. So what we do is we calculate what is called the percent yield. So the stoichiometry calculations we've done so far, we've said if I have this definite amount of compound A, here is the definite amount of compound B that should result from that. That's called a theoretical yield. So theoretically, if I take this much of A, I should get this much of B. But what if we weigh our product and we don't actually get that much of B? That's where we get that percent yield. Okay, so we have our theoretical yield. So that's what we calculate from the balanced equation. Okay, so theoretical yield, calculate. From balanced equation, okay? And then the actual yield, it's the amount of product you actually obtain. So you weigh this out. Weigh product at end of reaction. And then our percent yield is our actual yield expressed as a percentage. Okay, so what could cause these numbers to be off? Again, we could get impurities, we could have an incomplete reaction, we could get a side reaction, a product that's impure, maybe we weigh something incorrectly. Okay, so let's look at an example here. All right, so we have the silicon carbide. So we're going to take sand, we're going to react with powdered carbon, we'll get some carbon monoxide and our silicon carbide as a side product. Okay, so here's our sand. There's our carbon. We get our silicon carbide. And then we get our carbon dioxide. I'm writing things too fast. Okay. All right. So when we look at this, now we can balance our equation. All right. So take a look at this and see if you can balance the equation. Oh, it would help if I didn't write CO2 because I've been doing carbon dioxide in too many things. Another one of the classes I teach, we were using carbon dioxide a bunch, so it's kind of. All right, so if we look at this, I have silicon dioxide. So I have two oxygens there. My carbon monoxide, I'm going to need a 2 there. I have one silicon, I have one silicon. So silicon carbide has 1 carbon, 2 carbon monoxides means I'll have 3 carbons there, okay? So we're going to process some sand. We're going to get some silicon carbide. So we want to see what our percent yield of this is going to be. So first step is to calculate that theoretical yield. And that's going to be from the balanced equation. So we'll put it all together. We'll go from grams to moles, moles to moles, moles back to grams. Use those molar masses. All right, so we're going to get 100 grams of silicon dioxide. Our molar mass is 60.09 grams for that 1 mole. Our molar ratio, 1 mole of silicon carbide for every 1 mole silicon dioxide, and then we get 40.10 grams of silicon carbide for every 1 mole. All right, so we get a theoretical yield of 66.7 grams of silicon carbide. Now, what we're told is that we recovered 51.4 grams. So that's our actual yield. Okay, so our actual is the 51.4 grams. So to get our percent yield, we take our actual over our theoretical times 100. So we're going to take 51.4 grams over our 66.7 grams times 100, and we're going to get 77.0% is our yield. So there are whole fields devoted to just trying to get percent yield up on important industrial processes. So that is percent yield.